Hey guys, how's it going? Terry Brown, Mechanical Engineering here with another Engineering Mechanics lecture video. In this video, we're going to look at the moment of a couple. So let's get into it. Okay, so objectives of the lecture this time is to define what a couple is, understand that a couple or a moment is a free vector, and then we'll do an example to determine the moment of a couple. Some simple applications here. So fairly intuitive, right? If we need to turn this wheel and it requires a torque of 12 Newton meters to rotate the wheel, which one of the two grips of the wheel above will require less force to rotate the wheel? And then in each case, what force is required? So I think you probably know from experience that if we move our hands further apart here, we require less force to turn the wheel than if we try and turn the wheel with our hands closer together. So what force is required? If we need 12 Newton meters of torque or moment to turn the wheel, then you may or may not know, and this is what we'll look at in this lecture, is force times the distance between will give us the torque. So if we do that, we see that we have 30 newtons for the first one required to be exerted, and for the second way of applying the forces or the moment, we need 40 newtons in each hand. All right. Also, we have something like this where we're trying to tighten or loosen the nut on the wheel. What is the effect of changing the various dimensions here on the force that must be applied? So in terms of the torque or moment that we're exerting on the nut, if we extend this thing out here, it's not going to change anything in terms of the torque that we apply to the nut. If we extend these, then we'll increase or decrease the force that we need to apply. One thing that could happen is if we don't exactly have equal and opposite forces, then we have a resultant bending moment about this length. So increasing this distance here, C, will increase that bending. But anyway, that's all for future consideration. Let's have a look at defining the moment of a couple. So firstly, using scalar formulation. And I think we'll only do scalar formulation in this lecture. So a couple is defined as two parallel forces with the same magnitude but opposite in sense and separated by a perpendicular distance here, D. So just shown in a planar way here, we've got force here, equal and opposite force, and separated by a perpendicular distance D. And then showing it in 3D, and again taking note of the right-hand rule. So you can see that these forces here will generate a turning moment that's anti-clockwise if we look down, and using our right-hand rule, we'll see that the vector moment is upwards and perpendicular to this plane here, or if we're looking at the page, it will be anti-clockwise, so the moment will be out of the page. All right, the moment of a couple is defined as the force or the magnitude of each of these forces times the distance between the two forces. The net external effect of a couple is that the net force equals zero, fairly obviously, because we've already defined that these are equal and opposite, and the magnitude is F times D, which we've already said. So one of the important things to understand about moments and couples is that they're a free vector. So what does that mean? So if we look at this couple of forces here, two forces equal and opposite, I just haven't put the minus sign here. I've shown by the direction of the force that it's going in opposite sense. Right, separated by a distance D gives us an anti-clockwise moment or couple. So if we now take moments about an arbitrary point, so we've looked at calculating moments using the scalar method before. So we can choose any arbitrary point that we like on this plane and take moments about that point. Right, so if we do that, we have this one up here. The moment effect of this force is about point O is the force times D plus A, going anti-clockwise, and the moment effect of this force about point O is F times A. So if we do the maths, we end up with F times D, right? Which is what we defined on the previous slides. Right, so we could have taken, let me get my pen just quickly. So, we could have made point A up there and taken moments about that point. Right? We could have put point A over here, could have put A all the way down here, and we'd still end up with F times D. So what that tells us is if the point that we take moments about is arbitrary and we get the same result every time, then conversely we can apply this anywhere, right, and get the same result. All right, so continuing on. So M, as I said, is independent of where we take moments about, indicating that a couple can be placed anywhere on a rigid body, get my laser pointer here, and have the same external effect on the body. Okay, so it's important that we remember that it's the external effect, not the internal effects, and we'll talk about that in a little bit more detail shortly. Right, so for example, what do we mean by external effects? So we haven't done in this subject equilibrium yet, but you should have done it previously in Introduction to Mechanical Engineering and possibly physics. But so if we apply a moment like this, so when we look at moments applied to a component like this, we should really think about it as being applied like this, as two forces equal and opposite separated by a distance. Even though we draw an arrow like this, it's probably helpful to think of it as a couple like this that's generating this moment. Anyway, so we can apply that at the center of the beam, and we would calculate our reaction forces here. We could apply the couple at the left-hand end of the beam, calculate the reaction forces, apply the moment or the couple at the right-hand end of the beam, calculate the reaction forces, and in all three cases, the reactions at the supports will be the same. As you can probably realize, right, there's no applied forces here apart from what's generating the moment. So for this to be an equilibrium, right, the force here at the pin joint and the force at the roller here must be equal and opposite. And the magnitude of those forces will be determined by the magnitude of the moment and the distance between the supports. Right? And hopefully you can see that you'll get the same result in all three cases. All right, so it has the same, so that's what we mean by external effect. So we're looking at statics and equilibrium in this subject. If we were doing dynamics, such as you would do in, what's the subject called? Machines and Mechanisms A, if you're at UTS, then the way this would rotate and fly off into space or do whatever it does in dynamics will be the same no matter whether you apply the moment here, or at the right-hand end. What will be different though are the internal effects such as the stress and strain. And in this subject, we'll be calculating stresses and strains. The other thing that will be different, of course, will be the deflection of the beam, right? So if we apply the moment in the middle, it'll deflect in a certain way. If we apply the moment at the end, it'll deflect differently. So that looks like an external effect, but it's really counted as part of the internal effects because it comes from the strain that's developed in the body. In textbooks, you'll often see problems like this with applied moments. I already hinted at this. You'll see moments applied arbitrarily on these kinds of components. When you look at these kinds of problems, you probably should think about these as couples. When you see a force applied like this, you can kind of understand where that comes from, right? There might be, a weight sitting on. There might be a weight sitting on here, for example. There might be a cable pushing or pulling on here, whatever. Right? Whereas the moments, we think, well, where does that come from? How does that get applied to this thing? So these problems in textbooks are fairly arbitrary, I guess. Not arbitrary, abstract. So you really need to be thinking about, well, where does this come from? And as we go through the subject, hopefully you'll get a better idea of that. In the examples I did previously on the 3D vector formulation of a moment, I looked at that in the example too. So, and at the end of that, I looked at how the two bodies interact with each other. So if I drew a free body diagram of just the rod, right, and said, okay, applied to that rod would be a moment like this that's generated through that connecting mechanism that we looked at, or that connecting component of the mechanism. Anyway, let's have a look at an example. So again, it's fairly abstract example, but it kind of illustrates what a couple is and helps us to understand it a little bit better. You wouldn't really have a practical problem like this, but anyway, let's go through it. So we've got two couples acting on the beam, and the resultant of the two couples is 0. So we're asked to find the magnitudes of the forces P here and F down here, and the distance D here between those two cables that are attached to that beam structure. All right, so our plan to solve this problem, firstly, is to use the definition of a couple to find P and F. Right? So, as I said, it's not really that practical a problem. It's just to illustrate couples. So here we've got two forces equal and opposite separated by a perpendicular distance, so we can find P from the definition of a couple. And over here we've got two forces, same direction, equal and opposite, separated by a perpendicular distance. Right? And the way we'll do this is to resolve these angled forces here into X and Y directions, or X and Y components, and find the moment effects of those. And then determine the net moment and equate the net moment to 0 to find D. All right, so let's get into that. So from the definition of a couple, as I said, for this to be a couple, P here must be 500, equal and opposite to what we've got over here, and F must be 300. All right, so now let's resolve the 300 Newton forces here, the one here, and equal and opposite for the couple, into horizontal and vertical components. And we do it like this. Now, I always draw my components like this. So if I had have asked you to draw those components before showing you this, what many of you might have done would be something like this. We might have gone, right, there's one component, and then done that. Or you might have gone, let's do this one down here, and drawn your components like this. All right, so typically that's how they show you to do it in physics and in high school, because what happens is, of course, you get your right angle Pythagoras triangle here. All right, but what this does, if you do it like this, is it moves these components off their correct line of action. Right? So if we go to my version, so the line of action of this component is now where it should be, right? It's passing through point B. It's not up here somewhere. Similarly, down here, the line of action of the vertical component is through point A where it should be, not out here somewhere. So if you're into the habit of drawing your components like this, I recommend, I recommend that you get out of that habit and try to remember to draw them like this so that your components are going along their correct lines of action. So once we've done that, use your Pythagoras theorem to work out, and trigonometry to work out those values. If it helps, you can just draw a line, light lines. So often this is what I do. It's just to draw light lines like this. So it just helps you to work out which is cos and which is sine in our calculation of our components here. So here's 30 degrees. So the opposite is this side here, which is our horizontal component. Yeah, so just draw your light line so you can actually see your triangle if you want to, if that helps. But actually draw your components where they should be. Once we've got our components, it was given that the net moment equals 0. I'm just going to change back to laser pointer. So taking the sum of the moments, note I haven't indicated here the point that I'm taking moments about because I'm just adding up all of the couples, right? Because I've got 3 couples here, right? So this one out here, the 2 horizontal original forces, and now we've got a couple, the horizontal component at B and the horizontal component at A, they form a couple, and the vertical component at B and the vertical component at A also form a couple, so we can just add up all of the couples. Right? So that's what I've done here, and our only unknown is our distance between the vertical components of the forces at A and B here. Take note of the signs. So I've indicated that anti-clockwise is positive, which is the strictly correct direction for moments if I've got X positive to the right and Y positive vertically upwards. So this one here is tending to rotate clockwise. Hopefully you can see that. So if we push here and pull here, or pull at the top, right, that's going to be rotating around in that direction, which is clockwise, so negative. Then the 2 vertical forces here at A and B, that's pushing up, that's pushing down, so that's going to go that way. And then we've got the 2 horizontal forces at B and A, and hopefully you can see that they're going to tend to rotate around that way, which is clockwise, which is why we've got the negative here. Solve the equation for D, it's just some simple algebra. Rearrange that equation and we get D is about 4 meters. Okay, so let's have a little bit of more of a think about this. So let's assume we don't know about couples and we just calculate the net moment of the forces about some point. So I'm going to take point C, which is what you might often need to do. So I've just defined point C here at the center of the beam at its left-hand end. Right, so using our knowledge of calculating moments in the scalar form and using what we found before, using P equals 500, F equals 300, our distance here was 3.9645. And in order to calculate moments about point C, we need to know this distance here between A and C, which wasn't given, so I'm just going to assume it's something, right? An arbitrary value of 1.5. You can try a different value and see if you get the same answer. All right, so let's do the sum of the moments. So now, in writing the equation for what I'm doing, I need to indicate here that I'm taking moments about point C. Okay, in my when I write the formula or the equation. Right, so sum of the moments about point C, taking anti-clockwise as positive. Let's work our way through the forces. So we've got the 400 Newton force here times 0, and it's times 0 because its line of action, hard to draw a straight line with the mouse, but you get the idea, right? So anyway, you get the idea, right? So that force passes through point C, so 0 perpendicular distance. Then we have P times 2 going tending to go clockwise about point C, so negative 300 cos 30, so this force here, times D plus the distance DAC that we've assumed here tends to go anti-clockwise. And if you're not sure, again, just grab a ruler or a pen or whatever, and just put your finger or hold the ruler at the point where you're taking moments about and just push in the direction that you're taking moments about and see which way it goes. Right? If it goes anti-clockwise, it's positive. If it goes clockwise, it's negative. So we continue to work our way through all of the forces and we end up with an equation like this. So we just need to substitute our values from up here. So F is equal to 300, P is 500, our D's that we got up there. So put that in And hopefully, if you do the maths correctly, you'll get 0. Right. So as an exercise, redo this analysis, but take moments about point A and then take moments about point B, right, and see that you get 0 in all 3 cases. That took a little bit longer than I expected it to, because I explained more than I expected to explain. So hopefully that was all helpful and useful, even though it was a bit longer than could have been if I just went through it without explaining everything. Anyway, catch you in the next video. Bye for now.